Alrighty, we're going to take a look at a few more topics here in the covalent bonding section. And first up, we've got bond length. And so you see here, it's the distance between the nuclei in a bond. And again, we're talking about covalent bonds, so we're talking about the distance between the nuclei of two atoms sharing electrons. And you can see here, determined experimentally using X-ray diffraction and or molecular spectra. But if we're looking at single covalent bonds, we can predict them to a pretty high accuracy by looking at the radii of the two atoms involved in the bond. And you can find this information online, or you see here, this is the little table from your book on page 358. But if I want to know the bond length of the carbon-chlorine single covalent bond, then all I have to do is look at the radius of the carbon atom, which is 77. Whoops, didn't mean to cover that for you. 77. And chlorine is 99. And when I simply add those two numbers together, I get 176. PM is standing for picometers, not in the afternoon. Just kidding. Picometers. A picometer is 1 times 10 to the negative 12th meter, so obviously a pretty small distance. And then you can look on the chart there on the table, and you can see nitrogen is 70, oxygen 66. So the single bond between a nitrogen and oxygen atom, 136 picometers. And then your little teeny tiny hydrogen, 37 picometers, and added to a much larger phosphorus atom of 110. And you get a bond length of 147 picometers. Again, for single bonds, you could predict this. Not that they would potentially ever really ask you to do this on the AP exam, but we can sometimes compare bond lengths, as we'll see here shortly, between single, double, and triple bonds, and also with resonance bonds. And so let's look at that. Here we have this topic of bond order, which, if you're talking about two atoms, it's the number of bonds between the atoms. And if you're talking about a molecule, it's the number of bonds divided by the bond regions for the molecules. So here we see two carbon atoms. If there's a single bond between them, that's a bond order of 1. Double bond, bond order of 2. Triple bond, bond order of 3. Nothing earth-shattering there. As far as the lengths of the bonds are concerned, you can see that our double and triple bonds are shorter than single bonds. The bonds get shorter as you go, and we'll talk about that with molecular orbital theory. When we're forming those pi bonds, it pulls the nuclei closer together. And with the shorter distance also comes more strength, and we'll see that when we talk about bond energy coming up. The asterisk we will see here in a moment, as far as we can have non-whole numbers as far as bond orders are concerned. So again, when you're looking at a molecule, you're talking about bonds divided by where we see the bonds, bond regions. So let's look at a couple examples here. First, on the left, CH4, methane. I see that I have 4 single bonds, 4 bonds, and they're found in 4 different places, 4 bond regions. So for this molecule, 4 divided by 4, I have bond order of 1. Pretty much, if you have bond order of 1, whether it be for a molecule or for just between two atoms, we're talking a single bond. In the next picture over here, I see this compound with a carbon, a double bonded oxygen, and 2 hydrogens. And I notice I have 1, 2, 3, 4 bonds, but this time they're only found in 3 places, 3 regions around the carbon atom. So this molecule has a bond order of 1.33. And when we have fractional bond orders, it typically indicates we've got multiple bonds, or perhaps we have resonance. Molecules that exhibit resonance will definitely have bond orders in the fractional or decimal area. Here's our good friend ozone. And again, if I put ozone into the NMR spectrometer and evaluate it, I do not find oxygen-oxygen single bonds with a bond length of 132 picometers. I do not find oxygen-oxygen double bonds with a bond length of 114. I do find these oxygen-oxygen hybrid resonance bonds with bond length of about 123 picometers. And so again, we're seeing resonance. These oxygen atoms are in place. They do have a fixed position, and we'll talk about that in molecular geometry coming up, but the distances between them are not single bond length, they're not double bond length, they're in between. And so the bond order, as you see here, I've got 3 bonds located in 2 different regions around that central oxygen, and so the bond order is 1.5. Our friend the carbonate ion, again, I do not see carbon-oxygen single bonds, I do not see carbon-oxygen double bonds, I see 3 bonds of in between, and so those are our resonance bonds. And here I see 4 bonds in 3 different regions, so again I see 1.33. And so as it says here, resonance bonds will have a fractional bond order. But if you have a fractional bond order, meaning or decimal 1.33, 1.5, 1.67, that does not mean that the molecule has to exhibit resonance. Okay, we saw that example on the previous slide where you could just be having a double bond. But if there is resonance, expect a fractional or decimal bond order. Alright, so again, we have bond energy associated with our covalent bonds, and so you see the average enthalpy change for the breaking of a bond in a molecule in the gas phase is what we call the bond dissociation energy. And you typically have lists or tables or charts of these, and you'll notice again that up here with our single bonds, when you compare the double and triple bonds, those bond energies tend to be much higher as those bonds are stronger, and you get more energy released when you break those bonds. Now, you should hopefully be familiar with this diagram. Okay, again, when we're bonding 2 covalent atoms, here for example hydrogen, they have a certain potential energy when they're separated, and then as you move them closer together, there is that attraction between the nuclei and the electron cloud until you get to the perfect distance, which is the bond length, the internuclear distance. If you remember from our previous chart, hydrogen teeny tiny 37 picometers, so together the distance is 74. If you smush them too close, then the energy spikes and you actually end up in the repulsion zone. But right here we defined that this, with the potential energy dropping, that's the bond dissociation energy, and that's where those values are coming from. And typically then, in general, we can find the delta H of a reaction by doing the sum of the broken bond energies minus the sum of the formed bond energies. So this is our 4th exciting way that we can calculate delta H. We can find it in a calorimeter, we can use delta H of formation values in a table, we can use Hess's law, and now we can use bond energies. Which one would you use? Depends on what the question is given to you. If they give you calorimeter data, Q equals MC delta T, divide by the moles of the substance. If they give you a couple different reactions, you need to add them up, Hess's law. If they give you delta H of formation values, then you would do our sum of our delta H products minus the sum of our delta H reactants. And usually we do obtain delta H from thermochemical data, but it's very possible they can give us bond energy tables and have us do it that way. And you will notice, just like delta H before, these values are in kilojoules per mole. And so let's look at an example. I will warn you, when you're doing these, it's the broken bond energies minus the formed bond energies. Your bonds are broken in the reactants and then they're put back together in the products. So previously when we did delta H values, products minus reactants. But here, broken minus formed, you've got to remember broken in the reactant side, formed on the product side. So here we see an example, methane reacting with chlorine gas to give us CH3Cl and some hydrogen chloride gas. Personally, I think it helps if you can see these bonds. And so a quick little skeletal sketch. of these molecules could be helpful. You don't have to fill in all the lone pairs, but this could be helpful. And then a little secret, what you could do, you could add up every single bond on the reactant side, every single bond on the product side, and subtract them, and you'd get the right answer. Pretty simple when it's a little problem like this. If it's a very complex molecule, then you might want to really focus on broken minus formed. Because if you look here, these three bonds in our reactants and products aren't changing. What we're really breaking are those two bonds, and what we're really forming are those two bonds. And so technically, broken minus formed, I'm breaking a CH and a Cl-Cl bond, and I'm forming a CCl and an HCl. So I would use that data from my bond energy table, and I would get negative 104 kilojoules per mole. And so there we see exothermic heat is released, because they could always ask us, what type of reaction is this based upon your delta H calculation. If you had left those three CH bonds in, each CH bond is 413, so there would have been an extra 1,239 on each side. They would have canceled out mathematically, and you would have gotten still negative 104 kilojoules per mole. Now typically our thermochemical experimental method is the way to go, and we find that it's negative 101 that way. Our bond energies tend to be slightly off, but nothing to lose sleep over. Again, you would calculate delta H based upon what they give you. But as far as delta H through the eyes of bond energies, what are they telling us? And so you see, bond energy is most useful for explaining our heats of reaction. In general, if we have an exothermic reaction, weak bonds in the reactants are being replaced by strong bonds in the products, aka your products are more stable, and so that extra energy is being released. And vice versa for endothermic. We'd have to put a lot of energy in to break the strong bonds of the reactants, and we're replacing them with weaker bonds on the product side. And so when we get into next semester, I'm sure you remember those energy diagrams with the hills and our activation energies for every reaction. But an endothermic reaction would end up being easier to reverse because it would have a lower activation energy as opposed to exothermic. And again, we'll talk way more in detail of that next semester. But that's just kind of where this is going. But again, this is helping us understand the stability of compounds. And I'll leave you with this. Perhaps you've seen of or heard of a contact explosive. On that paper there's a mixture of nitrogen triiodide and ammonia. And that those two compounds, they're stable enough to be a solid right there, but just by touch, just by touching it with a feather or a stick, just by giving it that little bit of push to push the molecules close together, there's a huge explosion. And you can look that up on YouTube. I showed it in class, but what's happening is the bonds that are there right now are very weak. And what's going to be formed are nitrogen-nitrogen triple bonds, which are extremely strong and stable. Nice line. And iodine-iodine single bonds, which again are strong and stable because that's how iodine exists on our planet in the diatomic state. But so with this reaction, your product bonds are way stronger. The product is way more stable. Exothermic reaction. Alright, I hope this helps with those three topics. See you soon.